Okay, any questions about what we want to do? What I'll do is I'll start off with a review. The basic review is going to be really, really quick, but it's a chance for you to ask. So, review. Okay. So we started last time with canonical quantization. Canonical quantization, we define the states by creation and annihilation operators, a dagger of P acting on empty state. We define a field which is a quantum object. So phi is the integral d3p, 2 pi cubed, 1 over 2 omega. There's in the a of p, e to the minus I p dot x plus a dagger of p. And all the dynamics was in the time development operator, ui, well, infinity to minus infinity is what we use most of the time. So propagating from time minus infinity to plus infinity. And we took that by expanding that, we got the Feynman rules. Okay, so sub 2 is Feynman rules. And so we have things like, when we have that, we write minus I m is minus 6I lambda. So that's lambda phi to the fourth. And when we see this, we see propagator I over p squared minus m squared. Okay, so those are that's one whole development. And so for some people, these Feynman rules is the content of field theory. However, if that's it for you, it's not really sufficient. I mean, that's Feynman rules is good stuff. It's good for calculations of a lot of things. But the insights of field theory need much more than just the Feynman rules. And a lot of what we do this time is beyond that. So the second way we did it was by path integrals, where we have this z of j. It looks like a much more formal object, is z integral d phi e to the I integral d4x, the Lagrange density of phi d mu phi plus j phi. And that's the vacuum-to-vacuum amplitude in the presence of a source. So what you're doing is you're tweaking the vacuum and seeing how it responds. So it's vacuum-to-vacuum amplitude. And you can read out of this various things. So for example, matrix elements. Come out of this as, so here's an n particle Green's function of x1 up to xn is gotten by minus I to the nth functional derivative of z of j, delta j of x1 all the way up to delta j of xn. And then you drop the constant z of 0 and said j is equal to 0 at the end. Okay. So each time you differentiate, it brings down a factor of phi. And so that turns into time-ordered product of phi of x1 up to phi of xn. So those Green's functions are related to matrix elements. And the pictures that come out in perturbation theory are things like this. Here's x1, x2, x3, x4. So you get something where they scatter once. There's a minus 6i lambda that sits there. Then you get pictures that look like that, loop diagrams, all those are x1s, etc. And if you Fourier transforms these guys and you drop the propagators, that gives you the matrix element. Okay, so let's just say it again. If I Fourier transform G, I pictured G4 of x1 up to x4. That turns into I over P1 squared minus m squared, I over P2 squared minus m squared. For those propagators, and minus I m, and so I get the same old propagator. Okay, so by disturbing the vacuum here, by pushing on the vacuum by these various j's, I get to see how these fields interact. Okay. Any questions about that step? That's clearly not trivial, but we can go through it if you want. And then there's a bunch of techniques. What number am I up to here? I should be up to... Oh, yes. 6. At the very last class, we did a very short unit on the connection. But let me just remind you what it was. It's called the LSZ reduction. And it says that if I take matrix elements in canonical quantization, so in canonical quantization, the matrix element would be something like A dagger P1, A dagger P2, then A of P3, A of P4, times the time development operator. So the canonical quantization way of doing that is that matrix element. And this goes over in LSZ techniques by writing A in terms of the fields. A, you can invert from the field to A's, and you end up finding out that it's the product over all the fields of something that looks like integral d4x e to the I p, I'll do p3 since I've got that one there, dot x, times D'Alembert-ian x3 plus m squared, product of a lot of guys like this, times this 4-point function, x1, x4. Okay, so this part here is the Fourier transform part. The d squared plus m squared means you drop the propagators. And then what's left over is the matrix element. So the connection, there's a formal connection that goes through this. Now, this is something that's almost never used. You can, I don't think I've ever used it in a research calculation. Okay, it's not something that you use on a daily basis, but it's a piece of logic. And if you read the quantum field theory book that does path integrals, starts with path integrals, there's a logical gap in that book always. And the gap is solved by this. And the gap is that you don't know, in path integrals, you start off not knowing how to define your states. What are your states? And so if you're trying to get out matrix elements, if you don't know your states, it's hard to get it out. Once you know the answer, you can sort of pull it out by looking at that Green's function and just doing a calculation. You see you get the matrix element out. But to prove that that's the exact matrix element, you need this step. Okay, so this is the logical connection that makes path integrals, hooks up path integrals to our definition of our states, the usual things that we do. Okay, so it's not used, but it's logically important. Okay, questions on that? Yeah. And then finally, there's a set of techniques. We have another theorem. That tells us that if we have a symmetry, we have a constant current and charge. We'll use that a bit more, so hopefully we'll get good at that. Loops, there's a whole set of techniques on loops. I understand that we didn't do that in enough details for everyone to feel confident about it, but we'll do a bit more of that. And renormalization. So we did it as identifying the physical parameters. And then we have a side effect. Once you do that, there's no infinities left over. But the modern way of thinking about it is independent of infinities. It's just identifying the physical parameters. So there's my lightning review. One whole semester in that. Yes?
Do you plan on doing the form factor in more detail than last?
Which form factor?
Just
The idea of a form factor.
Yeah.
I probably have a couple calculations related to that. It's not a unit by itself. It might be an example. If you want me to work something in there, we can chat about it and I can work it in. You know, for example, in two places I can think to do it is in the E and M section. You know, when we do QED in a little more detail, I can work on that. And the other place is in the effective field theory. It's a standard calculation in effective field theory is to calculate the Q-squared dependence of some matrix element. Okay? Okay. So any other questions before we start? I actually am going to have a little bit of a review because I'm going to do the vacuum polarization three ways. Okay. And the purpose of this is to deepen our handling of path integrals, really. So the first way, I'm just going to do the Feynman rules again. And that's just really to set the stage for what I want to get out in the other way. The second way I'm going to do it is the way we did it last semester, but since you haven't seen this example, it'll be new for you, which is going to be a path integral treatment, but with the tricks delta Z, delta J type tricks. Okay, so the way we did it would have done it last semester at the end. And the third way, I mean, there's also a path integral, but is going to be the determinant of d squared plus m squared. So this is a new beastie. So we'll explain what that is when the time gets there. But it's an exercise, at the very, very least, at making sense out of an immensely formal object, turning it into a real calculation. Okay, so remember, here's the context I'm going to do is I'm going to do a charged scalar field. So phi is complex. You can write it as 1 over the square root of 2, phi 1 plus phi 2. So it's like two real fields. We'll use that fact a couple times. The Lagrangian is d mu phi star d mu phi minus m squared phi star phi. And then, since this is E and M, we put a quarter f mu nu, f mu nu. D is the covariant derivative. D mu is d mu plus I, the charge, a mu, and I'll often just use the symbol E for the charge. Okay. So we should all be able to read Feynman rules off this. The rules, if we have, so the field here then has a phi, and then there's a linear term in A. So P1, P2. And momentum, Q, I have it, my notes have it flowing in at the moment. Okay, so in doing this, there's one A, that's the field, there's then one derivative, so it's proportional to momentum. If you work it out, it turns into minus IE P1 plus P2 mu, which is minus IE 2P1 mu plus Q mu. That's Q. Okay. And then the second Feynman rule in that is the one with A squared. It's just A on one connected to A on the other with two phi's floating around. So it ends up being something that looks like that. One of these carries index mu, one carries nu. And they're contracted in the matrix element, so the rule is minus 2IE squared G mu nu. Okay. Now, aside from factors of 2, I can get you the factor of 2 if you want. That's just the fact that there's two A's there. So there's two permutations. Everyone comfortable with what those rules are? Okay, the first one is momentum dependent because there's derivatives and an A. The other one has no momentum dependence. Okay. Okay, so when we do the propagator for a photon, we have something that looks like that, plus some interactions, which for the moment, let me just put the blob there, and we keep iterating this. To get the full propagator. And for this guy, this thing that's the blob has the following pieces. Okay. If we go back, there's a one with a photon interacting with two scalars, and one with two photons interacting with one. So the types of things you can do is you can do a photon here, a photon there, a scalar there that hooks up back to itself. Or you could do a photon coming in, splitting up into two, going back to a photon. The initial rules there, one is of order e squared, the other is of order e. And I see a mistake here. That should be a factor of e right there. And I had two i's for people that weren't looking as I snuck it up, i.e. And so those guys, and let me call that A, let me call this B. The formula for A is pretty simple to write out. You take d4k, you take the propagator I over k squared minus m squared times the and I actually have, let's go back here. I'm pretty sure that's plus IE. My notes conflict here and there, but I'm pretty sure I checked it in the second case. So if you miss me doing it, I just flip that to a plus I, and I'm pretty sure that's right. Okay. Not that we're not going to work it out in detail, but that's, might as well try to be right if we can. Okay. In B, diagram B, we do the following. It's integral d4k. Sorry, 2 pi to the fourth go over there. 2 pi to the fourth. I have minus IE at the first vertex. It's 2k plus q if this is momentum q coming in, mu. I over k squared minus m squared. This is k. I over k minus q squared minus m squared. For the other one, that one can be k minus q going the other way. And then 2k plus q nu with a minus IE sitting there. Okay. Anyone want to ask about factors in that? There's no ordering issues here because this is all scalars. Those are just numbers. They can go in any order. I could write them in any order. When we do fermions, you have to watch out for the ordering, but this is just numbers. Okay, and the results. The results, I write this function is called pi mu nu. It's the vacuum polarization function. It's a function of the momentum of the photon going in, which is q. By gauge invariance, it's constrained to be of the form q squared g mu nu minus q mu q nu times some scalar function. So q dotted into the thing has to give 0, and we showed that it's a word identity. Pi, the scalar function of q, is some constant piece, pi of 0, which turns out to be uninteresting, plus pi hat of q, where this pi hat of q is. I will use the numbers later on, so let's just do it. It's alpha over 60 pi q squared over m squared when q squared is much less than m squared, and it's minus alpha over 12 pi log minus q squared over m squared for q squared much bigger than m squared. So last time when we did it, we actually did it for fermions, not the scalar. I did it in fermions. In fermions, this is a factor of 4 bigger. This scalar is 1/4 the size of the fermions. Otherwise, the numbers are the same. I think the way to explain it is somehow particle, antiparticle, spin up and spin down. Somehow gives the factor of 4. The log piece we used when we did the running coupling constant, so that the log running of that piece feeds into the running coupling constant. That's not the focus of what I'm doing here, though. I'll be using the first one more, the q squared less than m squared, because this calculation will also be a good example of one of our first calculations of an effective Lagrangian. So I'm going to do that here a little bit later on. Okay, certainly not today. Okay, and the other thing which I'll do, so let me just remind you of it, is when we did renormalization, this was the reason why pi of 0 doesn't make any difference, because it gets absorbed. We define our renormalized fields by if we start with our bare field, z3 to the 1/2, some renormalization constant, the renormalized field. Then the renormalized field is the one that has the right normalization, so we're just going to redefine the normalization, and z3 turns out to be 1 plus pi of 0 plus dot dot dot, and done very carefully, it's 1 minus pi of 0. 1 over 1 minus pi of 0. Pi of 0 then disappears from the rest of the world. It's irrelevant. And pi hat is relevant, but nevertheless, that's where it goes. And we'll do this again. We'll do it in a novel context when I'm doing the path integral, because I'll write the result of the path integral keeping A explicit, and you'll see that it has the wrong normalization. When I change the normalization, I get rid of this. Okay, so that's where one of the things that we do in the example. Certainly not this time, probably next time. Okay, so there's pathway number 1. You do the Feynman rules, you just turn the crank, and you're done. Okay. Next door. Get these lights back. Okay. So, again, any questions on that piece there? All right. Let's then try it by functional differentiation. Okay. And this is a little bit long, but it illustrates enough things that it's worth, I think, doing it carefully. So, we want G2, it's a two-point function, a function of x1, x2. It'll carry two indices. Actually, I'm sorry. I skipped a page in my notes. So let's hold this for the moment, because I needed to review what the path integral was. So this is a review of path integral. Okay. So the place we started was doing the finite dimensional integral. So z of j, in this case, is defined as integral dx1 up to dxn e to the minus I 1/2 xi aij xj plus ji xi. So there's summation convention there. And this is some matrix aij, which is n by n. There's n indices there. And by doing that, that's your classic Gaussian integral. This turns into, it's 2 pi I n over 2. The determinant of a to the minus 1/2 e to the minus I over 2 ji aij minus 1 jj. Okay, so there's, and the way you do it, just to remind you, is you can diagonalize the matrix A. That turns into the product of eigenvalues when you do the Gaussian integral. The inverse is just the inverse of the eigenvalues, and then you go back to your original basis, and this is then true in any basis. Okay, so there's our basic Gaussian integral. And then in field theory, so xi turns into a function of x, and it's the integral I that runs from 1 to n that goes into position x. So it's a continuous, it goes into an infinite dimensional one. The sum over I then turns into integral d4x. The matrix A turns into a differential operator, which in the case of a scalar field will be del squared plus m squared. The integral dx1 dxn is given the symbol d phi, the integral over all the fields. And a minus 1 ij, that turns into the inverse of the operator A, which is the Feynman propagator, x minus 1. Okay, so it's the thing that we end up using here is it's a function of two of these variables, so two positions, x and y, and it's the inverse of that operator. Okay? And there then come to be two basic results. Okay. If I have, so number one, if I just have integral d phi e to the I integral d for x phi some operator it's funny, it's not on my screen, so I don't know what I can do about it. Well, let's
I think it usually goes away.
yeah, has it been up there before?
Yeah.
Oh, it has.
Yeah.
It just goes away. All right, let's have it go away then. Ah, good. Go away. Okay. How many times has it been up there? I have seen it, I guess, because I get this little flash in the corner of my eye. Has it been doing this that much?
No.
Not that much. All right. So, is it when I start speaking? Boo. No, it didn't work. All right. So this one is some differential operator, which is actually typically going to be something like this. And by our little analogy up here, it's like doing this integral with j is equal to 0. So it's just the determinant. So this is some number which we don't care about, the determinant of O to the minus a half. And that's the new guy, the one that we'll explore a little bit down the road. The one that we used, however, is this number 2. The basic result is if I have z of j as the integral d phi e to the I integral d 4x of, in this case I'll write out a particular example, d mu phi minus n squared phi squared plus j phi. That's a j. Okay, that's the first piece is the differential operator, which will turn into del squared plus m squared. The second, the j. But when we're doing this, we're interested in the j dependence, so there's some constant out in front which we don't care about. Then the exponential of minus I over 2 integral d 4x d 4y j of x propagator x minus y j of y. Okay, so the j a inverse j is a function of two positions. I and j are positions, so it's a function of x and y, sums over all x's and y's, and the inverse is the Feynman propagator. Okay. So there's the two-path integral formulas. So actually, I'm back here because this is where I want to do the vacuum polarization by functional differentiation. This uses formula number 2. There, the one with the z of j. Okay. So this is then minus I squared over z of 0 del squared z of j j mu. I'll explain that. Delta j mu of x delta j nu of, so one is x1, the other is x2. Okay. So z here, let me just for the moment forget about j. I'll come back and put that in soon. Let me just do the free field case. Then z is the function of j mu is the following. It's integral dA mu dA some index e to the I integral d4 x minus a quarter f mu nu minus j mu a mu. Actually, let's make it plus j mu a mu. Okay, so each time you differentiate j mu, you bring down a factor of a. Okay. Now, to put this into a standard form, what we're going to do is we're going to write integral d4 x minus a quarter f mu nu in the following form. It's the integral d4 x, all right, is 1/2 a mu o mu nu a nu. Okay, so if we remember, we had phi operator phi. Here our fields are a's, so this operator o mu nu is what it is what sits in there. Okay, it's a differential operator. It has 2 derivatives. Now remember, since f is d mu a nu minus d nu a mu, it's the derivatives on a. To put it in this form here, what I might do is I might take a derivative that sits over here. So there's a d mu a nu sitting over here. I take the d mu, I integrate this by parts. I put the derivative not on this a, but on that a. So it becomes something that looks like d nu, d mu, a nu. So the first term there, in fact, turns out to be D'Alembert g mu nu. So sitting up there. So what we're doing is we're integrating by parts. And then the other term, it's antisymmetric. Well, d mu, d nu. Okay, so the other term comes when I take the derivative mu here acting on, it's this term here, d mu, d nu on a nu. Okay, so you either get D'Alembert box, del squared, on a field, or you get 2 different derivatives, d mu, d nu. And there's If you do the second term, you get the same thing. So the 1/4 goes to a half, and the minus sign becomes a plus sign by integrating by parts. Okay, you want any more workout than that? That's how it goes. Okay. Now what we're going to come back to later, but ignore for the moment, is the fact that this operator here has no inverse. Okay, so when we start the gauge theory section, the first thing I will do is come back to the statement that O mu nu has no inverse. Okay, and that's part of the issue in gauge theories. Okay, so we'll come back. But the answer to that, after we do it, is after we fix the gauge, then this O mu nu goes to some O mu nu prime, which is just D'Alembert-G mu nu, just the first term. Okay, and the inverse is the propagator that we normally use, df mu nu. Okay, it's the photon's Feynman propagator, which is just the usual propagator 1 over q squared with a g mu nu there. Okay. So, and the cheater's way, the wrong way, but nevertheless an okay, to get you the answer for today, is I could impose the gauge d mu a nu equals 0, so this term drops out, and I'm just left with that. To do it right, we'll do it right when we get there, but that's the basic effect. Well, because we really have this path integral over all a's still going on here, and it's not only those guys. What we'll do is we'll fix the gauge. That's why it's called gauge fixing. And we will do that. Well, that's why I'm postponing it. Yes, but we'll in E&M doing this is perfectly okay. It works out perfectly okay. It gives you the right answer, and there's no mistake that you make further down the road. If you did it in Yang-Mills or in gravity, you actually make mistakes down the road. Okay, so the right way differs from the naive way in more complicated theories. In E&M, it's exactly the same. Okay, so for now we're going to ignore that, and then if you just take the same old formulas that we have, then Z0, the free field J mu, is some normalization constant e to the minus I over 2 integral d4x d4y J mu of x Feynman propagator mu nu of x minus y J nu of y. Okay, and if I then do this differentiation, the g2 x1 x2, when I differentiate with respect to j, I bring down the Feynman propagator. You collect all the factors, it becomes I df x1 minus x2, which is what we always picture by just this. x1, x2, it propagates from there to there. Or for photons, we draw it as a wavy line, but it's just the propagator. Okay, so there's the free field limit. This Green's function is just the Feynman propagator. And we, of course, now we're going to decorate it by doing perturbation theory and the full theory. Okay. So the full theory. Okay. So Z J mu J is the integral dA d phi star. Okay, we've got two fields, phi 1 and phi 2, or you can take it as phi and phi star. There are two independent fields, so there's some two-path integrals if you want. E to the I integral d 4x. There's the minus a quarter f squared piece, which we just talked about. There's the d mu phi piece. So one's d mu phi star, d mu phi, minus m squared phi star phi. And then we have the j mu a mu piece, j phi, and j star phi star. Okay, so we've got two fields. They can be treated as phi and phi star, or phi 1 and phi 2, but we will add a source for each of them. Okay. One of the nice things about the path integral is that this can be factored, and we can save the A integration for later. We can take all the A stuff that only involves A, d4x, minus a quarter f squared plus j mu a mu, pull that out in front, and then much of our work now is going to be on the second piece. d4y d phi squared minus m squared phi squared plus j phi plus j star phi star. Okay, so there's the piece. And the two ways of doing this now is I'm going to, this time through, do this by the functional differentiation technique, where you will use the trick of functional differentiation to write this in a form to solve this, basically, that part. And the second time through, I'm going to solve it by using the determinant trick, that of some operator, and we'll solve it that way, make sense of that. Yes?
You can do this only because you have a simple group for the gauge, right? You are, I mean, separate the
No, it's just because these are no longer operators.
but if you have for instance, that you treat, the field A carries the base on the group, so
Yeah.
it doesn't commute.
No, actually, it's still fine for that. So the comment was that in other groups there's a charge in here also. Okay. But you'd still be able to do the separation, because this is really just a functional here of the field phi with a parameter g, the coupling constant. And this will have the coupling constant, and also it'll be more difficult to do some of these tricks because of that extra coupling constant. But it doesn't change the fact that this is just a function. This is a function of phi and A, but this is only A, so anything over here that involves only A can be pulled out outside of this integral. Okay. So it really just relies on the fact that these are just functions. at this stage. There's no ordering issue, there's no operator issues. And so if this is a function only of A, it can be pulled out. This is a function of phi and A. So I couldn't shift this to that side because there's an A dependent sitting in the covariant derivative. But I can factor this stuff out because there's no phi dependence there. Okay? So our focus initially is on this. And then after we calculate this in either of two methods, we're going to go back and take two derivatives with respect to this j here to get the Green's function. Okay. There's no j out here, it's just sitting there. But there is a over here. Okay? So, now the A dependence on this, if there was no A dependence here, this would just be a number, and we'd just drop it. It would fall out. So we're really interested in the A dependence after we've done that, the integration over phi. So the A dependence sits in two types of terms. So let's just write out the d mu phi piece, d mu phi star, d mu phi. Okay. Again, there's a piece linear in phi and a piece in A, a piece quadratic in A. The piece linear in A is minus I e a mu. It's phi star d mu phi minus d mu phi star phi. So that's the piece there. This is the current, the electromagnetic current of the field phi. So I'll just call that J phi for the moment. Unfortunately, it does get a little algebraically complicated. And then there's an E squared a mu phi star phi, and then the d mu phi. The piece that is independent of A. Okay. So we'll want to do perturbation theory. So sitting up here, there's a piece linear in A, in E, there's a and E, piece quadratic in A and E, and a piece that has no powers. So we'll expand in terms to powers of order E. Okay. So we have then okay, so the terms that actually turns out to be linear in E turns out not to contribute. I'm just going to write down the 1 and the order E squared piece. We get this e to the I action that depends on phi, which is this e to this guy up here. Is that. So just to avoid me writing it over, is 1 plus I integral d4y e squared a mu phi star phi, and to get order E squared piece out of this, I have to go to second order, so I have to take two terms. Let's make it it's then minus a half from expanding the exponential. d4 x, d4 y, d4 z, minus I-E a mu at y, j phi at y, minus I-E a nu at z, j nu phi at z. Okay, we're still up to that, plus dot dot dot, and then all this is multiplied by e to the I integral d4x d mu phi star d mu phi minus m squared phi star phi j phi plus j phi star j star. Okay. So I've expanded these pieces, but I have to keep this to all orders in the exponential because there's no small parameter. Okay, we clear on this? Okay, so this, at this stage, sits inside the path integral here, d phi star. But now we'll do a functional trick. Tricks galore. Here comes the basic functional trick. Okay, is if I have phi of y sitting in front of this exponential integral, all that stuff. Okay, that's equal to minus I delta j of y sitting in front of the exponential. Okay. So we have a phi sitting here. I can replace that by delta j. The jx on this exponential brings down a factor of phi. So that has an xy, so I've brought that down. Okay. I do the same thing for phi star. So the point of this functional trick is that I can take this phi that sits here and that phi star, the phi's that sit inside of the j's here, there's a lot of terms there, and replace them by functional derivative with respect to this j here. And once I do that, it no longer depends on phi, so I pull it outside of the functional integral also. Okay? So that's the point of that trick. Okay, so that if I have this integral d phi star 1 plus phi's, d4y plus minus a half, other stuff. Okay, so all that garbage there, e to the I integral d4 x, all that garbage there, it can be written in the following way. Replace all those with functional derivatives. I pull them outside of the path integral, so it becomes 1 plus I integral d4 y a mu, these are at y, delta j of y So the second derivative with respect to j. That's the first term. The second term is a minus a half integral d4y, d4z, minus I e squared times a mu of y. And then there's going to be lots. There's an a nu of z. And then there's a lot of terms here. I almost hate to write all these terms out here. All right, let me do the following. Let me write it as j mu as a function of delta phi, delta j. So in other words, wherever you add a phi, you replace it by j. Okay. And then we're left over with the integral d phi star e to the I integral d4x d mu phi star d mu phi and then the currents j star phi star. Okay, so there's a lot there. I actually have one mistake up there. Maybe more than one. Let's rewrite this correctly. It's delta j of phi, delta j of y, delta j star of y. Okay, one's the differentiation with respect to j, which brings down to phi. The other brings down to phi star. Okay, so that falls in the category of trivial mistakes as opposed to conceptual mistakes. I don't think I have any conceptual ones. Everyone understand what I mean here? There are 4 terms in this. Each j had 2 terms as functions of phi and phi star, and so but anywhere you saw phi, you write it as the derivative with respect to j. Okay. So what we've done here by pulling this out is this is now our basic Gaussian integral. We write this as some number z of 0 integral, no, I'm sorry, e, let's write it as exponential. It's I integral d4x, d4y, j of x, Feynman propagator of x minus y, j of y. So you can do that integral to your Gaussian integral. One of these is j star, the other is j. That's one thing. And there's no factor of a half. And again, there's just a small counting factor. There's 2 real fields. They have the same propagator. So they sum. You get rid of a factor of a half. All right. And just looking at the clock, I'm not going to finish here, but let me go one more step and then I'll stop. Okay, and we'll come back. It gives me a good place to stop. At this stage, since I've done this, I can take the functional differentiation. I get, if I take derivative with respect to j, derivative with respect to j star, I'm going to set j is equal to 0 at the end. I just get the Feynman propagator sitting right there. Okay. Here, I'm going to have propagators that can connect these 2. And so let me just write out what the answer is. So overall, z of j mu that we're interested in is the integral d a mu one plus I integral d4y a mu, and that those two derivatives just turn into the Feynman propagator y minus y. Okay, then the next term is minus a half integral d4y d4z. There's a minus I a mu at y, and then a bunch of terms that look like derivative respect to y of the Feynman propagator y minus z, plus then there'll be Feynman propagator of z minus y, plus three other terms, and then at the other side is minus I a mu of z, a nu of z. Okay, and I need to put indices on here, and I'm missing them. Okay, so I'll write that out more carefully at the start next time. And then I still have the integral. No, I still have the action e to the I integral d for x minus a quarter f squared plus j mu a mu. Okay, so we've done a lot of work here, but we've gotten rid of, at this stage, of all dependence on the scalar field except its propagators. There are propagators. And where we're headed, you can sort of see it working. The first piece there is going to be something that looks like an A, and a propagator that closes like that. That's the propagator x to x. The second pieces are going to be ones that have A at y, A at z, and propagators that go between them. So we'll recover perturbation theory by the somewhat painful way, but that's how we get there. Okay. Given the time, I'm going to have to postpone the punchline of this till we get back. But these two terms will lead to the two terms in the vacuum polarization. And we'll pull out the usual result. And then we're going to go through this thing a whole nother way where we don't do this functional differentiation trick here, but we use the determinant trick. Okay. Some more tricks. Any questions before we stop? All right. Thank you. See you next time.
Do you have any examples next week?
No. No, so the plan will be next week. I'll hand out a homework, and it'll just be homework. Everyone gets a high grade if you do all the homework. So, the grades are not the issue, but the homework is designed just to get you doing some stuff. Yeah.
The homework from the previous course still online?
Pardon me?
Are the homework from the previous course still online?